Good day, everybody. This is Chris back again, and what I want to do now is I want to talk a little bit about some background information. So, we talk about the contemporary use of chemical weapons. The contemporary use of chemical weapons really dates back to about April of 1915. What was going on in April 1915 was World War I. And World War I was characterized by what was known as trench warfare, where basically soldiers were kind of entrenched. They dug big trenches. They kind of battened down, and you basically had two sides, okay, and trenches, and then you kind of had this no man's land in between the trenches, and people pop up and try to take pop shots at each other, and you'd have these big surges of people that try to cross no man's land to get to the other trench and take that area over. So it was a really kind of a stagnated kind of situation. And what happened was, for the first time in April, I'm not sure the exact day. It was, I believe, it's the end of April, like April 20, 22, 23, right in there. But anyway, what happened is Germans. Okay, so we have the German side here, and let's just say that I had the wind in that direction here, and the Germans actually had canisters. Okay, they had these little canisters that they opened up, and these canisters contained chlorine gas. They opened the canisters up, and then the chlorine gas left the canisters, and the wind took the gas across this no man's land, and the gas went into the neighboring, or into the trenches on the other side. And chlorine gas, chlorine's a pretty heavy element, so it kind of sunk down to the ground. So it kind of went nap of the earth, if you will, followed the ground down, and then you kind of have the trench here, like so. And then you have a soldier. These were British and I think French soldiers for the most part. So you have the soldier down here in the trench, and then you have this chlorine gas just kind of creeping along, and then it would just spill into the enemy trenches, and these soldiers would inhale the chlorine, and there were many people that were injured, many people that were killed, and many people that went on to suffer significant disability as a result of this. So this is the first time that these agents were used, and because the first agent that was used was chlorine, and because chlorine is a heavy gas under standard temperature and pressure conditions, the term gas had kind of stuck. And so whenever we talk about chemical weapons, we talk about nerve gas and mustard gas and this gas and that gas. And what I want to do here in this video is I just want to make sure that everybody's on the same page when we actually talk about physical states of matter, because a lot of the weaponized agents are in fact not gaseous under standard temperature and pressure kinds of conditions. They're not really gases. So this term gas, quote unquote, is more of a relic of history, if you will. So let's just go ahead and make sure, and this is just real basic, but whatever. It just gets everybody on the same page as I start talking, and it's very likely that I'll make the same errors in subsequent videos myself. Okay, so imagine, if you will, that this is maybe a scale here going up. Okay, and this is the enthalpy. Oh boy, throwing in some thermodynamics and kinetics there. So enthalpy is, let's see, it is H, I believe, is what enthalpy is, equals the internal energy of the system plus the product of pressure and volume. That's a real common way of defining the enthalpy. And let's just assume in this situation that maybe pressure and volume are more or less constant. So the enthalpy is really a function of internal energy. So as I go up, the system that I'm talking about is going to have more internal energy. And what does that mean to have more internal energy? Well, that means that different states of matter are going to happen. So if I start down here, my lower states of lower enthalpy, system enthalpy, or lower internal energy, and in general, okay, we're just looking at kind of a big picture here. I have a solid. Everyone knows what a solid is. And for the most part, it doesn't change its it doesn't really change its shape all that well to fit whatever container we want to put it into. Its volume is more or less constant, um, and it's characterized by very strong interatomic and intermolecular forces. So we have metallic bonding, covalent bonding, ionic bonding, and oftentimes you have some sort of a crystalline structure that develops. Okay, so it's solid, it's highly structured. Now, solids can do one of two things. Okay, if I get those molecules or those atoms, okay, and I give them more energy, the internal energy of the system increases. Okay, they kind of vibrate about an equilibrium. They have a little more energy, maybe that's heat or whatever. Whatever injects energy into there, a heat transfer is a really common way of doing that. But anyway, eventually what's going to happen is I'm going to overcome those strong the covalent bonds, the could be even really significant hydrogen bonding at low temperatures, what have you. But anyway, what's going to happen is as that energy increases, there's going to be a phase transition, and the solids, okay, can become liquids. All right. All right. And typically solids become liquids by melting. Okay, I melt something and it melts, becomes a liquid. And likewise, if I cool, okay, maybe a liquid cools off or the internal energy decreases, the enthalpy decreases, the vibration is going to decrease, and then the intermolecular forces or interatomic forces, whatever they may be, will dominate. Okay, and you'll go back down to your crystalline structure. So my liquids can become solids again, and we typically say that this is via the process of freezing. All right, cool. This is probably nothing new for most people that are watching these videos. Let's go up here to even a higher state of enthalpy, okay, and that is what's known as a gas. Okay, gases are highly characteristic. They're compressible. Okay, they can change their shape. The system of gas can change its shape, its volumes changes, it's compressible. Typically, gases don't experience significant intermolecular forces. So you don't have these really significant hydrogen bonds that are occurring and all that. You may have weaker intermolecular forces, the van der Waals, so something like a London dispersion force or something is weak in intermolecular forces, generally so weak that when we model most gases, we say that the gases don't really interact in any meaningful way, looking at the big picture. Okay, so to get a solid to a gas, solids can, typically what we say is that solids melt and become liquids, and then through the process of vaporization, liquids vaporize into gases. And this can occur at high or low temperatures depending on the type of molecule I'm looking at. Like, for example, water is a liquid, but water can vaporize, okay? It can vaporize or evaporate into a gas at room temperature under standard temperature and pressure conditions. Some things are much lower temperatures become gases. For example, nitrogen, helium, hydrogen. These all exist at liquid. They have a liquid state, but the temperatures are much lower. Okay, you're talking about a much lower enthalpy, much lower internal energy kind of system for them to become liquids. Okay, and then gases, of course, can become liquids through the process of condensation. All right, doing good. Now, a solid can actually move, okay, to the gaseous form. I can actually vaporize a solid. And you may not even go through you may not even go through the liquid phase. And in a lot of cases, if I have a solid that moves directly to a gas, under special situations, the term that we have for that is sublimation. So, for example, solid carbon dioxide, or what we call quote unquote dry ice, sublimates. Dry ice under standard temperature and pressure conditions becomes a gas, and it doesn't go through this liquid phase. And likewise, gases can become solids through deposition. Is typically the process where you kind of bypass this liquid phase. And then finally, gases can become what are called plasmas, and the plasmas are up here at the highest enthalpy system. And a plasma, to move from a gas to a plasma, or from any state of matter to a plasma, you have to deionize that. Okay, so basically, if you have an atom, okay, you have a positively charged nucleus, okay, negatively charged electron in some sort of quantum state around the nucleus, I can go ahead and give that electron energy, enough energy to disassociate it, okay, bump it up to a high enough, basically give it n equals infinity for its principal quantum number that ionizes it, tears it away from the atom, and then you have this kind of soup of nuclei and electrons, okay, floating around. That's what plasma is. So real high energy substance there. And then, of course, plasma can go through the process of ionization, okay, to become a gas again. All right, so this probably is nothing new to anybody. All right, so I just wanted to make sure that everybody's okay on the states of matter. So now let's go ahead and talk about some special cases, okay, that do come up. So the first special case is just to make sure that we're okay with the term vapor. Okay, when I talk about vapor, okay, vapor is the gas form. Okay, it is a gaseous form of a substance that's usually either a liquid or possibly a solid. Okay, under standard conditions. For example, water. I can vaporize water. Water can become water vapor. For example, steam. Okay, steam is an example of water vapor. Okay, so just keep that in the back of your mind. The next concept is perhaps a bit more complicated, and this is the concept of an aerosol. Okay, this is the concept of an aerosol, and an aerosol is a very tiny, it's a tiny collection. All right, it's a tiny collection of either droplets or possibly particles. Okay, droplets or particles, and these droplets or particles are suspended in a carrier gas. All right, this tiny collection, so I can aerosolize a medication, for example. When you see somebody with say asthma or COPD and they're using a breathing treatment, I'm actually aerosolizing medication. I have medication in little tiny drops of normal saline or saline. Now, there are some examples of aerosols, okay, and these are very common in chemical warfare, so just kind of make sure that we're okay. Smokes, okay, different types of smoke is an example of an aerosol. Fog is another example of an aerosol. Mists, yet another example of an aerosol. Let's see here, smog. All right, you have a smoggy air. You can have a cloud. All right, yet another example. Okay, and then this is an example that I'm going to just put down here because there's some special consideration here, and this is something known as a fume. Okay, the word fume is often used outside of the context of what fume technically means. So let's just make sure we're okay on the technical meaning of fume. Okay, so a fume is actually a metal. Okay, so when you talk about gas fumes, that's actually not the correct way of using that word. Okay, a fume is specifically dealing with a metal that has become a gas. Okay, so I vaporized the metal, and then that vaporized metal condenses, and it forms tiny little particles, okay, floating around in the air when it condenses. And then these tiny little particles can become inhaled and wreak all sorts of havoc. So that's what a fume is. A fume is actually a metal that is vaporized, becomes a gas, then it condenses into tiny, tiny little metallic particles that can then be inhaled. Okay, let's just do a couple of examples to make sure that we're okay. So we'll often say somebody was exposed to mustard gas, quote unquote. All right. So what does that mean? Well, when we talk about mustards, and I'll actually go more in detail into the chemical structure of the two major types of what a mustard is. Your sulfur and your nitrogen mustards are the two ones that we run into in chemical weapons, and there are also some medicinal uses for mustards, particularly when it comes to chemotherapeutic agents for different cancers, neoplasms. Mustard gas is kind of interesting. Mustard gas under standard temperature and pressure conditions is actually a liquid. All right, so it's not really a gas at all. It's a liquid, and you can get it on you, and it can cause all sorts of problems. However, just like water, water in a sufficiently warm enough environment, you have a collection of liquid water. That water then can evaporate and become a vapor. So just like in that case of water, mustard gas can also do that. Typically at about 65 degrees Fahrenheit. Okay, so under 65 degrees Fahrenheit, mustard gas is typically going to be a solid. All right, and then above 65 degrees Fahrenheit, it will be a liquid. All right. And then if I manage, so if I have maybe a weaponized device and I manage to heat that up to about 423 degrees Fahrenheit and above, I can actually cause mustard to become a gas as well. Okay, so in the case of a weaponized agent, I have a weaponized delivery system. I might run into all three states of matter: liquid, solid, and gaseous mustard. And I've got to be aware of that. You know, what is the environment? What's a weaponized device? What happened here? Are we primarily dealing with the liquid form and is more of a skin cutaneous absorption? Are we dealing with, was the weaponized delivery system able to heat that up and vaporize it into a gas, and now I have an inhalational hazard? So there are lots of different questions that come out of looking at the different phases of matter. Likewise, another example might be many of your nerve agents. Many of your nerve agents are in fact not nerve gases, but they are liquids, okay, under standard temperature and pressure conditions. All right. But they can also be vaporized into gases as well. So then it comes to, what are we dealing with? Are we dealing with an agent like VX, for example? VX has a very low volatility, which means it doesn't evaporate very easily, so it is very persistent. it sticks around as a liquid. And so when it comes to VX, you're going to be more concerned about walking into an area with this VX liquid that's all around and actually getting some sort of dermal cutaneous exposure. That's why VX is almost always referred to as an area denial agent. It's an agent that you can drop into an area and you can prevent enemy troops or whoever from moving into that area because this liquid sticks around. Whereas something like sarin, okay, something like sarin or GB is very non-persistent. It has a very high volatility, so it is initially a liquid, but then it evaporates rather quickly into a gas and goes away. So sarin, your primary concern, it might be that you will have inhalational exposure. So you can disperse this agent. You'll have a lot of inhalational exposure, perhaps some dermal exposure, and then within several hours, it will have evaporated and essentially left the environment. So people can then move into the environment. So the physiochemical properties of the agents and their physical state really determine a lot about how they can be used in a weaponized sense, and what the implications of managing a response can be. Okay, guys, I think I'm going to go ahead and cut it off here. As always, thanks for hanging in there.